All right, so here is the same problem that we did in, I think it's back in class 6, then we did it in class 8, and now we're doing it in class 10. So we did it with the summation of forces, the Newton's second law, then we did it in work and energy, and now we're going to do it in impulse and momentum. Yay! Where we had this block, and I don't like the fact that my paper is showing through, so let me fix that. Okay. So we have this block, and we're putting this 50-pound force onto it, and we're going to push it up the hill. And the box weighs 25 pounds. It starts from rest. This is 25 degrees right here. We're going to assume that it will move, so we're going to use the kinetic coefficient of friction of 0.2, and then this force is applied to the block with 15 degrees from horizontal, and we want to determine the distance up the slope that it goes when it reaches 3 feet per second. So we still have to do the friction, and so just to be consistent here, we want to do a free body diagram and the inertial body diagram here, simply to get the normal force and therefore the friction. But we're going to try to be consistent and try to encourage you to always be doing the free body diagram and inertial body diagrams. It's just really good practice for any time you're trying to set up a problem and not skipping steps. So we know we have the acceleration here going up the slope right there, but there's nothing in the y. So we don't technically have to do the inertial body diagram because we're only going to look at this direction right here. So here's our theta 1, and here's our theta 2, and here's our theta 1. Here's the normal force, and we decide the friction has to be going down because the thing's moving up right there, right? And so we do the sum of the forces in the y prime direction, mass times acceleration in the y prime direction. We happen to know that's 0. There's positive right there. So we go negative p times the sine of what? Theta 1 plus theta 2, and then minus w, the weight of the thing, times the cosine of theta 1, and then plus Fn equals 0. We stick all that into there, and what we have right here, this is actually, I'm actually looking at the wrong page right here, so that's kind of weird. Did I never fix this right here? I don't know if I ever fixed it. I must have fixed it. 1 second, I'm going to have to pause the video here. Why do I have the wrong? Okay, so this is actually from a different problem. I decided to use my book, the problem I use in my book. And how come I don't have that with all the numbers in it? That's odd. Okay, well, let me fix that. Let me pause that real quick. Pause for the cause. So I just wanted to get the numbers all straight out right here. So if we put in for the values right here, so we put this 50, and that's 25 and 15. This is 25, and that's the 25 right there. We end up getting the 54.8 pounds. We know that the coefficient of friction right here times that is 0.2 times our 54.8. So we end up with, I think it's like 10 point something, right? 10.96 newtons, okay? And so now we want to do our impulse and momentum here. So what we have is we have our 3 diagrams. So I'll move this out of the way. Here's our first diagram. Here is our impulse happening to the thing, and then here is our final. Right here, right? And so I would write initial impulse and then final. It's happening to the thing, and I also want to define what what my directions are, because we've got to remember that this is definitely a vector operation we have to have. So we need to define our coordinate axis. All right, so right here, the mass times velocity at the state 1 is equal to 0, right? It starts from rest. And then we apply a force right here, P, and I want to put onto this thing that I'm going to say that it's a constant force, so we can say P delta T right there. So it's not just the force; it's also it's also the time. We have a weight that's acting on here, but that also is an impulse. We have a force here that's normal, delta T, and then we have a friction force, delta T, tightly onto this thing. And then when it's done, it has mass times the velocity 2 coming up onto the thing right there. So it's interesting. In my book, I did use the prime designation, which I don't like doing it, but it's okay. So what we're going to say here is what we're going to end up finding for here, or we write out the equation first. Let me write out the equation. The big equation first is with a vector. Right. And then break it down. Let's do it in the x prime direction. So in the x prime direction, we have 0. And here we're coming up the slope right here, so we're going to have P times the cosine of theta 1 plus theta 2 times my delta T right here, and we are also going to have minus our friction times our delta T, and then there's also going to be minus W, but times the sine of theta 1 delta T, right? It's going to be equal to, that's all the impulses that are acting on here. And you'll notice that we go by the signs are directed by the distance, because remember, these are vectors. And then when it's done right here, we got the mass of the thing times the velocity at 2 coming up the slope. So I don't know why I shifted everything over here so far. So 0 plus, we know this is 50 pounds, cosine of, what is it, 25 plus 15, so that's 40 degrees. We don't know the time. That the friction force is going to be 10.96, also times the time, which we don't know, and then we know the thing is 25 pounds, and sine of 25 degrees, don't know that this. Now the mass of the thing is going to be 25 divided by 32.2, and the velocity we want to know at the end is 3 feet per second. So we will go through this right here, and we could find out how long this thing has been applied to it. And it's 0.1388 seconds. So not for very long. So that's not what we were looking for. We found time, but we want to try to figure out, it says the distance. We want to know the distance that it's traveling, but we have time. What we would like to do is to get the acceleration, right? Let's get the acceleration, and then once we know the acceleration, we can get the we can get what the distance is going to be. So it's going to be a two-step process as part of this right here, right? So I ran out of paper because I wasn't being very paper conscious as part of this here. So let's figure out how much, what the acceleration is going to be for this thing. Well, we have here's the final velocity and the initial velocity plus the acceleration times the time, right? So we have the final velocity is 3, the initial velocity was 0. Let's figure out what this acceleration is going to be, 0.1388 right there. So we can get the acceleration is just simply going to be that divided by that, or 21.61 feet per second squared. And now if we want to get the distance for the thing, we can use this version of the equation, of the standard kinematic equations, and go this delta S, right? So now we're going to be able to, since we have the acceleration and here is the velocities, so we'll say this 3 squared is going to be equal to 0 squared plus 2a, and then that delta, that distance is what we're going to get. I'm sorry, we just found the acceleration. So we have 21.61, and now we get delta S. And so we can find what the delta S is going to be, and we find that it's going to be 0.2083 feet. And we probably want to turn that into inches, so 2.5 inches. And that's the same thing that we got with Newton's second law and with work and energy. So here's the thing that we had to do, though. We had to use, we got time out of this, but we wanted to get distance, so we had to bridge that using kinematics, right? So we remember that kinematics was the study of the description of motion, right? Using position, velocity, acceleration, and time, right? But now we have forces involved that are causing the motion, so we can still use that kinematics, the stuff that we used in the first 5 classes, but now we're using it in conjunction with kinetics. So kinetics and kinematics are working together. One of the big things to note here is that we have this division in kinetics. Kinetics, right here. We have Newton's second law. We have work and energy. And then we have impulse and momentum. Newton's second law, we deal with forces and accelerations. Work and energy, we deal with forces, we deal with distances, I'll go x, and we deal with velocity, right? In impulse, we deal with forces, we deal with time, and we deal with velocities, right? So if these can kind of show you like which one maybe is more suited, which types of problems are more suited than others for this which method we're going to use. So some certain problems kind of lean towards a particular method. But as we go through, we'll also be on the lookout for methods that can't be used under some certain circumstances, where there's like really only one set is going to be the way to use. One method, a particular method, will be very attractive to using. For when collisions, much more of an impulse and momentum type of thing. So we'll be on the lookout for that as we're coming through. So that's all we have for this first example.